So arithmetic sequences versus geometric sequences, just to give you kind of like the 1,000-foot overview. Arithmetic sequences are what we just looked at on the previous slide. 2, 4, 6, 8, 10, 12, 14, 16, on and on and on. There are patterns where our rule requires adding the same number each time. Think arithmetic, adding. So our rule could be plus 5. Our rule could be take 10. It could be plus 100. It could be minus 1. And another thing I'll draw your attention to is our starting point could be anything. We could start at 100 and our rule could be minus 10, in which case our sequence would go 100, 90, 80, 70, ... because it continues. So our arithmetic sequences are like our addition and subtraction. Depending on whether in the rule we're adding or subtracting, will tell us whether like the sequence gets bigger or smaller. But again, it's going to form that like linear pattern because we're changing the exact same amount each time. However, our geometric sequences are a similar thing. They're sequences, they follow a pattern or a rule, but the difference is instead of adding like the same thing, which in the case of arithmetic sequences, we call that like the common difference. It's called D. In geometric sequences, we multiply by a common ratio. So we actually end up with like more of an exponential curve, which we'll illustrate a little bit further shortly. So geometric sequences, our starting term might be 3 and our common ratio might be 2. So I start with 3 and I multiply it by 2. So I get 6. I get 6, I multiply it by 2, and then I get 12. Multiply it by 2 to get 24, multiply it by 2 to get 48, multiply it by 2 to get 96, and you can see that every time it's doubling. Whereas our arithmetic sequences grew by the same amount each time, our geometric sequences grow kind of more like exponentially, again, is the word that we're going to use, because we're multiplying by the common ratio every time. So we're going to have a little bit of a look at the difference between those now. So arithmetic sequences, again, the next number can be found by adding the same number to the previous term. And the number that we add again and again and again is the common difference, which is D. And a little side note, D can be positive or negative. So again, our starting point might be 5 and D could be positive 2, in which case our sequence would go 5, 7, 9, 11, 13, ... Or if it's a negative, we're actually going to go backwards. But it's the same process. We're starting at 5, then we're going 3, 1, negative 3, because our common difference is negative. So it's important to keep in mind that our common difference can be positive or negative in arithmetic sequences. So how do we calculate it using recursion? This might look a little bit scary at first, but once we break it down, I promise it'll make a bit more sense. So again, T1, sometimes referred to as A, is the first term in the sequence. And this is the rule that we use to calculate or solve arithmetic sequences using recursion. So Tn plus 1 is equal to Tn plus D. Or if we break it down in words, that can help make it a little bit make more sense as well. So the next term in the sequence, Tn plus 1, is equal to the previous term or the current term plus the common difference. So think back to our example before, 2, 4, 6, 8, 10. Our term 2, for example, is 4. So if I'm going to say let n equal 2, then we can actually solve that out. T2 plus 1, that gives us T3, is equal to term 2 plus the common difference. That makes like perfect sense. Our next term is found by adding the common difference to our previous term. That's all we're saying here. And we'll do some illustrations to hopefully make that a little bit more clearer. So another thing to keep in mind, and I know this is a lot of new information, so it's okay if you have questions again still, because this is probably quite new content for most of you as well. So if our common difference is positive, the numbers will get larger. That's what I talked about before. It will get bigger, more positive. And the bigger the common difference is, the faster the growth. So for example, if I'm adding 2 every time, yeah, our growth is going to grow at a constant rate, but like it's still going to be slower. But if I'm adding 100 every time, we're going to grow a lot faster. That's just like how numbers work. And again, this is linear growth because we're starting at a number, adding the exact same amount, adding the exact same amount, adding the exact same amount. It's just going to keep going on forever, really, because again, we're just adding the same amount over and over and over. And again, that's how we're getting that linear growth in. It's following that same pattern, that same line. On the other hand, though, if D, or if our common difference is negative, our number will get smaller. And again, the bigger the common difference, the more rapid the decrease will be. And that's linear decay. So that's just some more terminology to keep in mind. And just like the general idea of if it's positive, you know, it's going to keep getting bigger. If it's negative, it's going to keep getting smaller. So we have an example to work through together. Consider the arithmetic sequence defined by t1 equals 3. Our first term, our starting point is 3. And our rule is tn plus 1 equals tn plus 4. So our next term, how to find the next term, you take the previous term and you add 4. And we're being asked, what is the fourth term? So I'm going to communicate this really clearly here over to the side in red to kind of illustrate that a bit better. So to substitute, we could say let n equals 1. So now you can see we've got tn plus 1. But if I'm going to say let n equal 1, we have t1 plus 1, which is t2. And that's equal to tn. And we've said n is 1. So it's equal to t1 plus 4. So now we can substitute for t1 because we know that our first term is 3. So to find our second term, we take our first term and we just add 4. Which gives us 7, but that's only our second term. So if we let n equal 2, we know that our third term is going to be equal to our previous term plus 4, which gets us to 11. And to find our fourth term, we take our third term, add another 4, and it gives us 15. So again, it's just that continual process of this is like the formula to make it like official, but all we're doing is adding 4 each time. We're taking the current number, adding 4 to find the next number. That's what we're doing. Another awesome little calculator trick to keep in mind, to generate a recursive arithmetic sequence using a calculator, what you do is you enter the number. Sorry, this should say enter the number. So you enter your starting point, which could be 5, could be 10, could be 27, whatever your starting number is, you enter that. That's your T1, term 1A starting point, whatever you want to call it. And then you press equals. And then you enter your rule, which because it's an arithmetic sequence, it'll be plus something or minus something. For example, it could be plus 2. And then you press equals. And that'll give you your second term. And because your calculator knows that you want to make a sequence, it's going to keep doing this the more you press enter. So you press enter again to get term 3. You press enter again to get term 4. And you just go on and on and on. And it just, yeah, if you keep track of how many times you've pressed enter, it can help you find like a sequence, like a term further on in the sequence, which is really helpful. So you can also graph arithmetic sequences. So I have 2 examples here. This is my first example. So this one here, T1 is 1. First term is 1. Beautiful. Second term is 3 because every time our common difference is 2, so we're adding 2. So we can see this pattern working out. 1, 3, 5, 7, 9. Similar calculations to what we were doing before, but just in a table form. And it's also been graphed. So this is how we actually graph sequences. So n is normally put along like the x-axis and tn is normally put along the y-axis. Just because like tn depends on n. So that's why we just graph it this way. So when n is equal to 1, our term is 1. When n is equal to 2, our term is 3. When n is equal to 3, we can see that our term is 5. When n is equal to 4, we can see that our term is 7. When n is equal to 5, we can see that our term is 9. So you can see that we graph sequences just like any other set of numbers. Here, for example, our starting point is 9 in this second example, and our common difference is -3. So each sequence, so each time we apply our rule to find our next term, we're actually taking away 3. So we're starting with 9, and then we're taking 3, so we get 6. And then we're taking 3, so we get 3. We take 3 to get to 0, take 3 to get to negative 3. And we can actually graph that on the same graph. So here you can see when n is equal to 1, our term is 9. So I've graphed that to reflect it. When n is 2, our term is 6. 3, 3, 4 is on 0, and then 5 is actually on negative 3. And you can also reflect a trend line to suit that. So what differences can you see here? Main thing I notice, or the few things I notice, is that this one, positive common difference, we can actually see that linear growth, same pace, straight line, increasing growth. Here, negative common difference, we can actually see the decay, the linear decay. It's decreasing by the same amount each and every time, which is really, really interesting. The other thing is this, even though there's only a tiny difference, we can see there's a more rapid decrease here because our common difference is bigger. And remember, the bigger the common difference, if it's positive, means it'll grow faster. If it's negative, means it'll decay faster, get smaller faster. So even this small difference of being negative 3 instead of negative 2, we can see that that's still influencing our growth. But what if we don't want to do recursion? What if we don't want to find term 1, 2, 3, 4, 5? What if we wanted to skip like straight to term 37? We definitely want to be able to have a much faster way to do that. So a general rule for finding the nth term of a geometric sequence, that's just kind of like the name for it, is the explicit definition, which is this here. So looks a little bit more complicated, but again, once we break it down, it's just a simple matter of like algebra and substitution. So as long as you're carefully showing your work, it should hopefully, as long as you're doing it step by step, you will be able to solve it. So it just takes some practice, which is totally okay. So again, Tn, our term number that we're looking for, is equal to T1, so our first term, plus the number of the term we're looking for, minus 1, multiplied by the common difference. So that's our formula. So if, for example, I'm looking for term 25, I'm going to say let n equal to 25, and as long as I know the right information, then I can actually solve and find my unknown variable. And again, this formula, like conceptually, makes sense in my head because we're saying, okay, the term number I'm looking for, it's equal to term 1, so our starting point, plus this many applications of the common difference. So for example, if we're looking for term 25, I'm saying to find 25, term 25, I'm taking term number 1 and I'm adding my common difference, 25 take 1 time, so 24 times. So I'm taking my term 1 and then I'm adding my common difference 24 times so that I can get to my 25th term. So that's kind of conceptually how I see it. But again, that may or may not make sense in your mind. But as we practice it a little bit more, hopefully the rule will start to make sense in your head. So the common difference for an arithmetic sequence is 16 and term 12 is 236. Find the first term. So here we've jumped straight into a bit of a trickier example. Whereas in our example before, the formula is arranged so that we're looking for Tn, our number. But here, I've given you our number, it's 236. I want us to find a different unknown. So here we're already using our formula in a little bit more of a complicated way by finding a different unknown. But same step, same process, same algebraic thinking. So Tn is equal to T1 plus bracket and take 1, close bracket, D. That's what we're doing. Always start with what do we know? Substitute in anything we know and always clearly define all of your variables because part marks for working is so important and so valuable. So make sure you're getting as many part marks as possible. So n is equal to 12. I know that. T12 is equal to 236. So n is 12. I know what term 12 is. And I also know that Tn is 236 and I'm told that common difference is positive 16. So what I can do substitute in for everything we know. Tn, we know is 236. T1, we actually don't know. We know that n is 12 and we know that d is 16. So now that I've substituted in everything I know, all it simply is solving step by step, following like the regular rules of operations. So again, that's why communication is so important, because if you do make a mistake somewhere along the way, there's still part marks available for like, working out operations and all of those sorts of things. And then again, so what we've done here, we've simplified in the brackets and then we've multiplied there because that's following our order of operations. And then by taking 176 from each side, we can actually find our answer for T1, which is 60. And if we've done that correctly, we'll actually be able to check it, like using our calculator, for example. So if I put 60 equals, and then plus 16 equals would give me term 2, equals would give me term 3. And if I kept going to get to term 12, if we've done this correctly here, that'll give us 236. Just another quick example. So a bakery produces 3 cakes every hour. Initially, there were 17 cakes. If Tn is the number of cakes after n hours, how many hours will it take to produce 300 cakes? So again, it makes, you could use recursion to solve this, but it does also make sense to use our formula. So here, this is actually, in my opinion, where it kind of like sequences gets the trickiest. So T1, I am actually saying is 20. And that's because, oh, I haven't defined n there, but that's okay. This might seem a little bit counterintuitive, but the interesting thing is, oh, here's where n is defined. If Tn is the number of cakes after n hours, how many hours will it take to produce 300 cakes? But this is really interesting. There were 17 cakes initially. So I had 17 cakes at the start when 0 time had passed. No time has passed, but we still have 17 cakes. But Tn is the number of cakes after n hours. So after 1 hour, we can make an extra 3 cakes. So after 1 hour, we started with 17 cakes and we've made 3 cakes. So T1 is actually 20 because this is saying n is equal to 1. So after 1 hour, we have 20 cakes. Or you could also define T0 as 17. That's another way you can like communicate that. But again, it's really important when it comes to word questions, you need to think about what is it actually asking me and how am I going to communicate it? There are a few different ways you could solve this problem, but you've really got to be careful about what you're actually defining n as. So that's where you need to be really, really careful. So common difference, positive 3. 3 cakes made every hour. And Tn, we want to know when it's going to exceed 300 cakes. So what I've done, I've substituted into my formula. I've expanded my brackets. 3 times n and 3 times negative 1 will give me plus 3n, take 3. And then I've simplified by doing my 20, take away my 3. I've collected like terms. I want to isolate n, so I've taken away 17 from both sides, and I've divided both sides by 3. So again, isolate n, get n by itself, which has given me n is equal to 94.3. And again, how many hours will it take to produce 300 cakes? That needs to be a whole number because it wants to know how many hours. Remember, n has to be a whole number. It can't really be a decimal. So I'm going to say after 95 hours, that's how long it'll take us to reach the 300 cake threshold. And again, asked in a sentence, always answer in a sentence. It's a great way to, again, make sure you're getting all the marks possible. So the 300th cake will have been produced by the 95th hour. And then you can actually always check by substituting that value for n into your original formula. And I can see here, in fact, that if we let n equal 95, then we can see that after that time, that we will have 302 cakes, which means that by 94 hours, we'd only have 299, and that doesn't like meet the requirements. So we do indeed have to wait 95 hours to have at least 300 cakes.